Hi guys, welcome to the first video in chapter 4 on really the moment of a force. Well, chapter 4 is called Force System Resultants. Okay, so just a quick, background. If you recall, in chapter 2, what did we do in chapter 2 is we simply looked at summing up forces, right? And then we calculated a resultant force. Then in chapter 3, we extended this to the matter of equilibrium, where actually the sum of the forces was equal to 0. Okay? So in the same idea of first looking at how to add up forces and get resultant forces and get force components, and then use that for the chapter on equilibrium, right? Remember, this was equilibrium of a particle, right? Now, in chapter 4 and 5, we are moving on to, we're now beginning to work with rigid bodies. Okay? So just take notice of that. Chapter 2 and 3, we were looking at the forces, and then chapter 2 prepared us for chapter 3, which was equilibrium of a particle. Now, chapter 4, which is called Force System Resultants, essentially is going to show us how to calculate something called a moment. Okay, a moment, and we will get into that in a minute. But a moment is really, we're looking at the rotational effects of a force. Okay. Whereas here we were looking at the translational effects of forces in chapter 2 and 3, meaning we apply a force and we're just looking at what happens to this particle in certain linear or translational directions. Okay, so x and y, and okay, I don't have to recap these two chapters, but now what we're doing is we are looking at the rotational effects that a force will have on a body. Okay, and the point is that chapter 4 prepares us for chapter 5. Let me just show you quickly. So chapter 5, let me just get chapter 5 here. It says equilibrium of a rigid body. Okay, so chapter 3 was equilibrium of a particle, but now chapter 5 is equilibrium of a rigid body. So it is very important that we really understand chapter 4 quite thoroughly, because it prepares us for chapter 5, which is equilibrium of a rigid body. Okay, so that's just a quick background. So chapter 5 is equilibrium of a rigid body. Okay, and obviously, if you understand what I'm actually trying to say, is that when we come to chapter 5, we don't only need all the forces to be equal to 0, the sum of the forces equal to 0. We need all the rotational effects to also equal 0 in chapter 5. Okay? But we'll get to that later. Now we're in chapter 4, and we're going to look at something called a moment. Now, what is a moment? What is a moment? Well, as I said in class, this is not that special time that you have with your significant other. That's not what we mean by a moment. But a moment, well, before I get to a moment, ask yourself, do you know what is the line of action of a force? If we have a force, right, say it's being applied to a body here. By the way, I want to just emphasize again, from chapter 4 onwards, we are essentially looking at bodies, rigid bodies, okay? Whereas chapter 2 and 3, particles. Chapter 4 and 5, bodies, okay? So keep that in mind. So if I'm applying a force here to any body, and what is a body? A body could be a laptop, a body could be a car, it could be a cup, it could be a beam, it could be whatever. A body is simply something that has mass and size, if you recall. Alright? So So here is a body, and we're talking about the line of action. What is the line of action of a force? Line of action of a force is simply the line that passes through the direction of the force in this way. And this is extremely important, guys, that you understand what is the line of action of a force. If you don't get the line of action of a force right, then your calculation of moments will be incorrect, okay? So again, the line of action is simply the line that passes through the force like this, okay? In both directions, okay? So you need to practice drawing these lines of action when you do the problem. Okay, so now that we've got the idea of a line of action, what is a moment? Well, let's just look at the textbook definition here. It says here, let's wait for it to focus, when a force is applied to a body, it will produce a tendency for the body to rotate. Okay? Remember I said now we're going to look at the rotational effects of a force. Okay? So a force is applied to a body, it will produce a tendency, okay? It not necessarily is happening, but it might be a tendency for the body to rotate about a point that is what? What is it? Not on the line of action of a force. Okay? So what is it saying? Just wait for this to focus. If I apply a force to a body, right, then there will be a tendency for this body to rotate about a point that is not on the line of action of the force. So a point there, a point there, point there, right? All these points are not on the line of action of the force. So if I apply a force to this body, then there will be a tendency for this body to rotate about any point that is not on the line of action of the force. Okay, look at this, for example. I found a lid. Okay, nice little lid with a crack. So if I apply a force here, can you see the pen? Okay, I'm applying a force. Can you see it is moving in that direction, but there's also a kind of a rotation there. Can you see that? Can you see that? There's a rotation. There's a rotational effect. Let me bring a ruler. Here's a ruler. I'm applying a force here. Can you see that there's a rotational effect? Okay. I apply a force here, and there's a rotational effect. Okay. And obviously we need to do a bit more analysis, but I'm just trying to give you a bit of a feel that you're dealing with moments every day of your life. When you if there's a door, okay, if there's a door there, there's the handle, okay, and there's some hinges here, and it rotates around this hinge. You apply a force by pushing there, but what happens is that because it's free to rotate here, it rotates about this point. But what happens now if you go and apply a force at that point there, that exactly the same force? You will get no rotation. Okay, so just try to see how this is applied in real life. That often we apply forces and it's actually causing a rotational effect at a point which is not on the line of action of the force. Okay, so that's the basic idea here. So a moment is the rotational effect. Okay, it is the rotational effect of a force on a body. Okay, and a moment is given by this basic equation in scalar form. Okay, remember we're doing scalar notation. M, moment, is equal to force times distance. So if I want to find out what is the moment about this point here, let's call it O. I've got my force, tick, very good. But now, what's very important is something, it is the D. What is the D? Okay, the D is known as your moment arm. Your moment arm, another textbook calls it your perpendicular distance. Okay? But what does that mean? So it's called the moment arm or the perpendicular distance. Now, what does perpendicular distance mean? It means, and that is why, guys, I'm emphasizing this matter of the line of action. Okay? Because the perpendicular distance or the moment arm is the distance from, if you put your pen on the point of rotation, this point O, okay, we want to see what is the moment about point O. What is the rotational effect of this, that this force causes on this body about point O, right? We put our pen on the point O and we draw a perpendicular line from the point of rotation to, listen to this, to the line of action. Okay? Not to the point of application necessarily, but to anywhere along the line of action so that I have a perpendicular line between this point and the line of action. Okay? So here's another body. Okay, let's say there's point O and I have a force there. I've got a force there. Right, that's the direction of, that's the point of application right there. And there's the direction of the force. So how would you draw the line of action? I mean, first of all, you need to draw the line of action, but how would you calculate just graphically the moment arm? Well, again, guys, line of action. What is the line of action? I draw the line of action, I extend it, and then from this point O, I draw a perpendicular line, and that becomes my moment arm, my D. Okay? What happens if I apply the same force there, for example, at that point in that direction? Then I extend my moment arm like that. Right? Sorry. I extend the line of action. Okay? And I draw my perpendicular distance like that. So from the point to the line of action, so that I have a perpendicular distance there. Guys, please practice that. Please. So what do you need to master? You need to master line of action, and you need to master the moment arm. If you get these two wrong, then everything else will be wrong. Okay? So this is the magnitude of my moment about point O is force times distance. Okay? So the force times distance. So it is the rotational effect. When I apply a force to a body and I want to determine the rotational effect of that force about a certain point, I need to multiply the magnitude of that force by this perpendicular distance. And the perpendicular distance is from point O to the line of action of the force, and it is a perpendicular line like that. Okay? Okay, so when we say, the next thing I want to mention is that moment is a vector, right? So when we speak about magnitude of a moment, the magnitude is simply equal to FD. Okay? It's this here, F times D. And D is our moment arm or our perpendicular distance. Okay? Now guys, students struggle with this every year. And I really struggle to explain this, but I really want you guys to get an intuitive feel here. Okay, hold on. Before we go on to direction, okay, I just want to look at some of these pictures here. So this is figure 4.1. Figure 4.1 here is a wrench. As you can see, there's a force being applied there, and this force causes a rotational effect. It allows us to loosen a bolt or something to that effect, okay? Or to tighten. And as you can see, there's a force and there's a D. What happens if we change the direction, the angle of that force? Right, there's my F, and now I've changed the angle of the force. can you see I need to now extend the line of action and find what is that perpendicular distance. Do you see that? Okay? And obviously in this case, my question to you is, in which case will the moment be larger? Which case will the moment be larger? Meaning, in which case will this force, remember they're exactly the same force, guys. Please get that, exactly the same force. This one is acting perpendicular to this line, and this one is now, there's an acute angle, okay? So it's no longer perpendicular. It's exactly the same force. But now, by changing the angle, the moment arm has changed. This moment arm now is smaller than that moment arm. So obviously this force here will cause a smaller moment, okay? And therefore this one will be more difficult if you're trying to loosen a nut, okay? So this one will be a lot easier because your moment arm is longer. Even though your force is the same, your moment arm is longer there, your moment arm is shorter there, and because M equals FD, this moment will be larger. So this will be a lot easier to open, okay? To loosen. What about this one? You see, if this is the point of rotation and our force is acting along the line of, the line of action of our force is passing through the point of rotation, then there will be a zero moment because our moment on D is zero, even though it's exactly the same force as these two ones. Okay? So, okay, I hope we're getting somewhere. Okay, so when I said moment is a vector, it has a magnitude which is equal to force times distance, but we also need to discuss the direction. Okay? And the direction is kind of not super intuitive. In two-dimensional space, it's intuitive. In 3 dimensions, it is not necessarily that intuitive. So, just to recap, the magnitude of our moment is F times D. Okay? But now I want you to look at this drawing over here. Okay? How do we determine the direction of a moment? So, let me just quickly come back here. When we're talking about the direction of a force, that's very easy to understand. You apply a force at that point on a body, and we know the direction of a force, right? That's the direction of the force. That's very easy to understand. When we talk about the direction of a moment, okay, it is essentially based on the right-hand rule, okay? The right-hand rule. So let's just go through some of the mechanics of it, and then we will look at the intuitive, deeper understanding. If I have a force there, okay, I'm applying a force about point O, I calculate my moment on D, and I'm able to calculate a magnitude. But now the direction of the force is based on the right-hand rule. Can you see this person's hand there? The right-hand rule. Put your fingers in the direction of the force and curl them towards O. In the direction of the force and curl them. Can you see that? They're curled towards the direction of O. And then your thumb goes up. Okay? So, fingers in the direction of the force and they get curled towards the point of rotation. Okay? So now, based on this right-hand rule, so what have we got here? Guys, 2 things you need to look at. The curl of the fingers and the direction of the thumb. The curl of the fingers and the direction of the thumb. Okay? In 2-dimensional space, the curl of the fingers gives us the direction. In 2-dimensional space, look at this picture here. There's the force, there's the moment arm, there's the point of rotation. Our fingers go in that direction and they curl towards the point of rotation, and then we're able to see, oh, okay, this force here is going to cause a sense of direction that is counterclockwise. anti-clockwise. Does that make sense? If I apply a force here, okay, maybe you're trying to see, okay, give me a real life example. Okay, I'm going to put the ruler down again, and I'm going to apply a force here. Okay, so can you see? Say my finger's at point O, and I've got a force there. My pen causes a rotation like that. Can you see that? Force down, it's causing a rotation. So there's my force. There's the point. Rotation, and it causes, it has a sense of direction which is counterclockwise. Does that make sense? Counterclockwise. Okay, there's the pen which is the force, here's the body, there's point O, and it rotates it counterclockwise. Okay, so now how do we determine what the direction is? We put our fingers in the direction, okay, the camera's a bit too close, but you put your fingers in the direction of the force and you rotate them towards point O, and the direction of your fingers, the curl of your fingers will give you the direction, the sense of direction. Okay? In 2D, two-dimensional space. Alright? Now, what if my finger here is point O and I'm applying a force there? Right? Can you see that the rotation, if there's my point O and there's my force, right, you would need to invert your fingers. Okay, I still can't do it because of the camera, but what you'll notice is that your fingers, you put your fingers with your thumb down into the table, and then your fingers will be pointed in the direction of F, and they will curl towards point O. And so, if we had the ruler here, and we applied a force there, can you see that the ruler would rotate in that fashion? Okay? So this is the two-dimensional way. And in 2 dimensions, because of the right-hand rule, our convention is that counterclockwise is positive. So what does that mean essentially? It means that if I'm applying a force like this on a body, okay, say the ruler, and there's my point of rotation, then my magnitude will be the force times the perpendicular distance, right? F times d. Calculate my d, I have to know my f. But then, because it's a vector, I need to give it a direction. So in two-dimensional space, we will have MO is equal to force times distance, and because it is rotating the body counterclockwise, right, anti-clockwise about point O, this value will be a positive. Okay? I forgot to mention the units are Newton meter. Okay? So what about this one? If there's my point O and I'm applying a force which causes the body to rotate clockwise, then I will have MO is equal to F times D, that's the magnitude, whatever F and D are, and it will be a negative because it is clockwise. It is in the opposite direction to this. Okay? So the right-hand rule in two-dimensional space, the right-hand rule allows us again to determine the sense of direction based on the curl of the fingers. All right? The curl of the fingers, like there. All right? Now, this will be the last thing. Now, that's in two-dimensional space. What about three-dimensional space? This is a little bit more confusing, and I just ask you to please try and think about it, because it's actually not difficult. Okay? What you can see here, guys, is a hand. Remember I said in two-dimensional space we look at the curl of the fingers, right? But in three-dimensional space we look at the direction of the thumb. Okay? So in three-dimensional space, when when we speak about the direction of a moment, the direction is given by the direction of the thumb. This is why it's less intuitive, because we have a force, and this force causes a rotation like that. But the way we define the direction of the moment is by an axis that is in the direction of the thumb, which is perpendicular to the plane that F and D are in. If I draw a plane, like this plane here, that includes F and it includes D, then the direction of the moment, guys, the direction of the moment is a vector that is perpendicular to the plane that F and D are in. Another way of looking at it, it is the axis about which this body is rotating due to the force. I'm going to repeat that. When we speak about the direction of a moment in three-dimensional space, it is the axis it is the direction of the axis about which this force is causing the body to rotate. Does that make sense? Okay? So in two-dimensional space, we look at the curl of the fingers. We look at the curl of the fingers. In three-dimensional space, in 3D, we look at the direction of the thumb. Okay? And what does this signify? It signifies the axis about which the body, so the direction of the axis. We're looking at the direction of the thumb, which is the direction of the axis about which the body is rotating. Okay? And it is a vector that is perpendicular to the plane of F and D. Okay? So, guys, when we talk about the direction of a force, it's very easy to understand the direction of the force. If I apply a force to a body like that, then the direction of that force is along the line of action. However, the direction of a moment is in three-dimensional space, it is the axis about which the body is rotating. It is the direction of the axis about which the body is rotating. Okay? So what is the direction of this moment in two-dimensional space? That's the sense of direction. It's anti-clockwise. But in three-dimensional space, what is the direction of the moment? It is the direction of this axis. Okay? So if this was the XY plane, then this would be the Z axis, and the direction would be K. Alright? It would be K, because K is the unit vector in the Z direction. Okay. So I'll get more into this a bit later, but please, after what we've spoken, please go and read over this and make sure that you understand it. Okay, we'll do some examples in the next video.